Okay, welcome everyone to the seminar hosted here at USC on behalf of the International Network on Quantum Annealing, INQA. Our speaker today is Arnab Banerjee, and he will tell us about annealing as a route to complex magnetic phase discovery. Arnab, please go ahead.
Thank you so much. It's an honor to be here and to meet all of you. So this talk is on annealing route to complex magnetic phase discovery. I am an assistant professor. I have been in Purdue for the last 2 years, so new. And before that, I was a scientist at Oak Ridge National Lab. And before that, I got my PhD from the University of Chicago. So the work that I'm showing here has been done by my undergrads, Akshat, Eliana mostly, and also by my graduate students, Guga, and also Paul Carries, who was working with Travis Humble, Phil Lostro, and then also with the help of Andrew King at D-Wave and Hayato and Avradip, who are my friends at Fujitsu. So as an outline, I will introduce the magnetic phases and phase diagrams, and then neutron scattering and susceptibility, something that we are trying to emulate. Then I'll show the D-Wave results, the Fujitsu results, and some recent QAOA results on the Shastry-Sutherland model on triangular lattices. And the main point that I want you to get out of the talk is that we have validated annealing for magnetic phase identification, and it works. And it can help us in material Hamiltonian identification as well as new phase discovery. And the main point is that every backend has its own unique features, advantages, and disadvantages. And it is powerful. The powerful approach would be to find out what the problem is and then fit the backend to it, is what we think. So why is the magnetic phases important? Well, we all know that spin phases of matter are very important because we got magnetic memories out of it. And magnetic memories happened because of the fact that it has a Hamiltonian which allows one spin, if it aligns in the one direction, the next spin also aligns in the same direction, the third spin also aligns. So there is an overall, formation of a cluster or a community among the spins. And for that matter, but that's only just one phase of matter, which is ferromagnetism. There are so many other phases of matter which are possible. For example, the topological phases, the skyrmion phases, new phases like spin ice, spin glass, spin liquids, and also emergent defects like domain wall and domain wall motion. And the question is that there are so many other new applications probably are possible from it. And to understand what are the new phases of matter which are possible and what are their applications, we have to first understand them. And going beyond, there are a zoo of new magnetic phases of matter, such as spin ice, which we see in dysprosium titanate. We can see valence bond solids, and then, of course, valence bond liquids and quantum spin liquids, which show very nice topological and non-abelian behavior, something which is extremely interesting. But then the question is that how do we really get there? So here we are exploring quantum annealing as a route to this phase discovery. And I got interested in quantum annealing long time back when I was working with Tom Rosenbaum, who was my PhD advisor, and we also talked a lot with Gabe Apley because he used to come and sit in our group. But the most important thing that we know is that in order to get to the right phase, we can do it in two possible ways. One is the quantum phase, where we change a quantum order parameter, the control parameter, versus the classical, where we change the temperature. And these are two slightly different ways of getting to the final phase. One happens through tunneling, and the one goes jumps over energy barrier. And as a result, you can actually get new phases in quantum dynamics which you cannot get in the classical. And there is a paper on this as well, which really got me going, because you basically avoid getting stuck in a local minima, and you can access the quantum states, and you can get close to the interesting states close to criticality. Now, of course, the hope is that we can emulate some of that in the new quantum computers which are coming up, and the annealers which are coming up. And we started with D-Wave because it was a very natural choice on the Chimera, where where what happens is that each of these dots on the D-wave chimera lattice is basically of a fluxonium qubit. And you have two control parameters there, the AS and the B, A as a function of S and B as the function of S, where S is the annealing parameter. And you have the Hamiltonian, and then you have a transverse magnetic field. And that's the Hamiltonian to solve. And then you have a quantum annealing term, and then you control S versus B as the ratio between them to find out what your final phase would be. So there are some very nice papers by the D-Wave group. One is that going to a 3D spin glass, and then the observation of topological phenomena in 1800 qubits by Andrew King, which was looking at the Kosterlitz-Thouless transition, which gave us hope that, look, we are really getting to the right place. And maybe there is, you are getting to this complex phases, which means that it's very difficult to get to these phases just with classical annealing sometimes. So maybe we are getting to the right spots. Then the question that I was trying to ask is, can we simulate a system where we can directly measure, can we simulate a system which we actually measure with neutron scattering or do some bulk susceptibility measurements? So since I'm an experimentalist, that's the question I started asking. So to give you a little bit of idea of what neutron scattering measures, it's a pretty scary equation here, but let me break it down for you. So the scattering cross-section basically has some constant. It has the magnetic form factor, which tells you whether you have a magnetic scattering versus a lattice scattering. It's a very important term. This is a term which is why we get such clean data using neutron scattering. Then we have a selection rule which says that only perpendicular components contribute, which kind of tells you whether you have an Ising system or a Heisenberg system, and so on and so forth. But the most important thing that we have is the Fourier transform of the spin-spin correlation. So the question is that whether we can get to that in what we do with this quantum annealers. And these measurements are done using the Polish neutron source at Oak Ridge National Lab. So I was a neutron scattering scientist there, and that's how I got interested in trying to understand some of the data with the D-Wave machine as well. But this is not the only neutron source. You have the Lujan Center, the ISIS at Oxford, Paul Scherr Institute, Spring 8, and so many others. And without going into too much details on how that works, I'll just say that what we have is we have an incident neutron beam, just maybe a little bit. We have an incident neutron beam which goes and hits a sample which sits right here in a crossstat, and then it goes and hits a detector. The detector is a huge drum which sits here, and you have a human being for scale. And where the neutron hits actually tells you what is the Q vector. So the Q vector is the Fourier transform of the spin-spin correlation function. So that's what we know. And when the neutron hits, it tells you what is the time of flight, and it tells you the energetic. So we get both the energy and Q information from here. And the detector is basically a 2D detector. And the way we get to the third dimension is by rotating the crystal. So it's almost like tomography is what we do. And then we construct an overall map of what the scattering looks like. And that's basically what we do. And when we do that, we can get to very, very, very nice scattering patterns that we get from quick condensed matter samples. For example, here we see pinch point scattering. Here, some people have seen pinch point scattering in dysprosium titanate, which comes from an all-in, all-out configuration of the spins. And as we know, there is a recent paper in Science by Cristiano Nisoli and others from Los Alamos, where they also see this pinch point scattering in a square lattice spin ice. So future experimental facilities will provide access to many such phenomena. And then we also need to have the quantum computing framework to basically match with that. So what we started working on is a simpler model called the Shastry-Sutherland model. And the Shastry-Sutherland model is a frustrated lattice where you have two different kinds of magnetic interactions. One is this blue dotted lines, which are along a square. And then you have this red interconnects in between them. And as you would see, that it is a frustrated lattice. And I'll come to that a little bit more. The reason why we started working with this is, first, this is a model which has been researched a lot, and the answers are already known, so we can benchmark against some known answers. And secondly, it's actually there it is realized in real materials like rare earth tetraborides in Erbium, platinum, lead, and can be exactly solved. The reason why this is a frustrated model is because you see these triangles. There is a triangle here, a triangle here, a triangle here. Each triangle is basically frustrated. The reason is that if you have antiferromagnetic interactions, J and J prime, then you know that in a triangle, if you have Ising spins, then you can never fully solve the triangle. So, I mean, you have basically three degenerate solutions where one bond is satisfied, the other two bonds will never be satisfied. So you will always have frustration. So if you just take this triangle and you extrapolate it to like a big lattice, like a Shastry-Sutherland lattice in this case, then all the bonds are frustrated. All bonds are frustrated, and you get like sometimes an infinitely degenerate ground states. Infinitely many solutions. Now, and when you apply a field, what that field does is that that field tries to ultimately push all the spins in a certain direction and have a ferromagnetism, but it happens through several more interesting phases, which look like magnetization plateaus. And so in the Heisenberg model, you see the magnetization plateaus as well, but you can also see them in the Ising model, where you see this 1/3 magnetization plateaus. So the question is that, do we see that? And this problem also has no sign problem in QMC. And as I was mentioning that this is a very, very, very interesting model, both in the Heisenberg limit and the Ising limit. In the Heisenberg limit, I had worked on this problem extensively back in my days where I had 3 PNS papers that we published where we discovered that one of these compounds, strontium copper borate, indeed has a dimerized ground state. But in the Ising limit, this problem is also very interesting, and we are working with Joe Chekleski's group at MIT to get some materials on which we are doing neutron scattering studies to figure out, okay, what would be the spin configuration and what kind of magnetization plateaus we can see. There are also some very interesting papers by Joe Chekleski's group and Art Ramirez. And how they look like this. So if you look at the magnetization, which is a sum total of all the spins versus magnetic field, you see this very queer magnetization plateaus, which kind of means that it's not a simple ferromagnet or an antiferromagnet. It goes through these jammed states of some spins aligned, some spins not aligned, and they're very regular type of states. The reason why it's regular is that if you sit on one of those plateaus and then you do a neutron scattering study, which looks at the overall correlation, then you find this kind of a 4-spin kind of pattern, which shows that these are indeed long-range correlated states. And the question is that can we achieve these results from a quantum device such as an annealer? So that's the basic question that we are working on. And my student right now is also working on measuring holmium tetraboride, which also shows these kind of states, these states. So we started working on quantum annealing with Travis Humble and also Paul Carries, who was Travis Humble's graduate student and also worked very closely with me, and Andrew King, and I brought the problem to them, and hence we got started. So, this is the unit cell for the Shastry-Sutherland lattice, and we found there are 2 different embeddings that you can do on the D-wave chimeras. So the first one is the tilt embedding, and the second one is the half cell embedding. And there are advantages and disadvantages of both, but we chose the half cell embedding just because it is very symmetric. There are 4 qubits required for every connector and every bond. So 4 bonds for every bond and 4 qubits for every spin. So the renormalization, should I say, is pretty symmetric. So, and that symmetricity is actually extremely important because we don't want to break the symmetry between the qubits. If one spin is like 6 qubits, one spin is 3 qubits, it generally doesn't work. Then in the shimming required is much more. So we went with the half cell embedding, which is this one, and then we embedded the whole pattern on the D-wave machine. And when we did that, we got this defective lattice, which if you translate, basically translates to this whole lattice of Shastry-Sutherland with some defects kind of there, because the D-wave lattice was itself defective. Following that, we did forward annealing, reverse annealing, as well as Markov chain, monte-carlo type annealing, which is the which is the quantum evolution monte-carlo, as some call it. And what we found, to our surprise, is that one of the answers is that magnetization is 0.3. That was the answer in one of the 1/3 phases. And what we found is that when all these parameters and the annealing step, the annealing depth, all of that are very, very nicely balanced, you get to the right solution in the very first iteration of this Markov chain quantum annealing or quantum evolution monte-carlo, in the very first iteration. That's it. So you do one reverse annealing step and you're done. You get the solution. So that was actually very heartening to see that it is possible. So, and how does the phase diagram look? Well, this is the phase diagram which is published by Dubliniak in PRL in 2012, and where we see the 1/3 phases, the Ising phases, and this is J2, which is the out of plane, which are the triangular bonds, and H is the magnetic field. And we did a cut right around there. And when we did that, this is what we found. So for high magnetic fields on both sides, we saw the ferromagnetic phases, and then in the middle, we saw the 1/3 plateaus right at 1/3 magnetization. And these are results from the deep wave, and we could also see the critical phases. And when we stitch together the entire phase diagram, can you see that this phase diagram is basically this upper phase diagram here? And these are the deep wave results indeed. And so it seems that we are getting the right states. These are the 1/3 plateau and the ferromagnetic phase, but we also see some new phases like 1/3 anneal, 1/9 that we were exploring. So overall, how does the spin-spin correlation look? So if we take the overall result of 496 spins and then we Fourier transform them, then what we find is that we can go from the ferromagnetic state, which is right now, back through a critical phase where we see this round-like pattern, into a 1/3 phase where we see this 1/3 plateau, going through another critical phase into the antiferromagnetic phase, back into the 1/3 plateau phase, and back into the ferromagnetic phase. So we could see all the phases which were indeed predicted in the Dubliniak PRL paper from 2012, using a completely different Monte-Carlo technique. So that was actually very heartening for us, that we can actually see the right things. But not only that, what was also heartening for us is we can get access to the critical phases and how the critical scattering would look if we can sit right on the critical point. And last but not, what we also find is that you can see this 1/3 plateau phase. This forced peaks that you see here kind of almost looks like the peaks that you see in the scattering that comes out. Well, the Q vector is not quite the same, but the nature of the scattering is the same. So those are the D-wave results. And we published that in PRX Quantum. And not only that, we did quite a few things which I can go over with you in a lot of detail, like how do we deal with the boundary condition, the shimming. But let's move ahead right now for the sake of time. When we were doing this, then so Hayato was at Fujitsu at that time, and at Fujitsu we have our Avradip Mondal, who was a school friend of mine, and he said that why don't you also see what we can do here, because there what you have is a parallel tempering mechanism which can also be very fast, and can we also do magnetic phase discovery using the digital annealer. Now, the digital annealer is it's fully connected set of 8,000 qubits, but it is classical. Everything is classical. I mean, we should not expect any quantum result out of it. And also what we should not expect out of probably a Fujitsu digital annealer is right at the critical point, if we have some long-range coherent states that you might have some chance of getting from the D-wave quantum annealer, we shouldn't expect it from the Fujitsu annealer, because the very nature of parallel tempering is that you are basically flipping several bits at the same time and to see how the energy landscape behaves. So when we did that, we were able to not only get some of the same phase diagrams that we saw using the D-wave machine on the Fujitsu annealer. So these are the results from the Fujitsu annealer. So if you look at, this is the J1, J2 ratio, and this is the magnetic field. And for a certain values of J2 by J1 and the magnetic field, you should get a magnetic dimer. And this is how the magnetic dimer looks on a 60 by 60 lattice. And this is indeed a dimer phase. In fact, if you stare at it long enough, you will know that for every upspin, which is black, there is a downspin, which is white, and they're it's a random dimer phase. And then if you decrease J2 by J1, you get to the anneal phase. But the advantage of having 8,000 completely connected bits is that we are not restricted to the embedding problem so much. It's all-to-all connected. So we can go to much more complex magnetic lattices and, magnetic interactions. So we basically had J1, J2, J3, J4, J5. So we had all kinds of nearest neighbor interactions and also the next nearest neighbor interactions, some of which we draw here. And when we do that, what we find is that we see a variety of phases which are very, very complex and extremely nice. For example, we discovered this 1/3 plateau phase, which is, we thought it is a very peculiar phase. As you see that it has a very complex kind of a coordination. I mean, you have a triangle upspin forward, but it's a very nice mosaic that we have. And not only that, what we found, so you can actually do, and these are all consistent with a paper which was published in PSSB in 2015, who were also trying to see what other kinds of phases you see in such a model and to explain some of the experimental results. There are two ways in which you can get to the result in here. One is by looking at the energy landscape, and one is by looking at the magnetization. What we found is that when the magnetization is all degenerate, then you can look at the energies, and just from the law of finite size scaling, from the law of first order phase transitions, discontinuity in the slope of the free energy basically gives you where the phase transition would be the first derivative of that. And we can actually use that technique to also figure out where our phase diagrams, phase boundaries would be. And that also matches another recent paper in Europhysics Journal published in 2018. So that was very heartening. And once we could do that, we were now able to kind of let loose and figure out whether we can discover any new phases. So we did discover a new phase for a set of parameters that we have shown here. Which is also an overall very interesting phase, which is, we found two phases. One is the overall solution looks like the staircase antiferromagnet, and then we found another phase, which is right here in green. It's a 5/9 plateau. But as you can see that it has a coordination over several spins. So these are very, should I say, very complex phases involving plaquettes, which are very, very large. And that was heartening to see that you could even see that. So that was what we found. And these results are now published in 2021 in the International Conference on Rebooting Computing. It's an IEEE journal, just published. And with the hope that now we can go and try and figure out what would the Hamiltonian, we can look at realistic Hamiltonians, like true 3D Hamiltonians, and figure out what would be the phase diagrams of matter. We can understand criticality and where the critical points are, and what would be the nature of the thermal and quantum fluctuations. How do we address that? And then there is also another very important research that we need to do, which we don't understand so very well in material science, but we hope that these very fast machines can help us. Which are, what are the size of defects? Can we actually deliberately put some defects on the whole structure and we can drive it to a new kind of a jammed phase? Does it change the Hamiltonian? And can we see some of the phases that are indeed seen by some of these other susceptibility techniques and neutron scattering techniques, or Raman, or whatever? And there are several ways you can actually change the whole, you can cook up your system, and I'm not going into too much details on these, but this is now published. And but one of the bottlenecks that we have so far is that everything that I was saying so far is in Ising lattices. What if your system indeed is not Ising? And that is what got us to researching beyond Ising. In fact, that's the dream, but we started with Ising here as well, which is using quantum annealing on quantum and quantum approximate optimization algorithms, that's QAWA, on similar kind of frustrated lattices. So this work was done by Phil Lostro who is a postdoc at Oak Ridge National Lab, and Hanjing Zhu, who is a fourth-year graduate student in computer science at Purdue, along with Travis Humble and Book Giles. And the hope is that we can get to the true quantum limits. So we are very hopeful that this paper will soon be published. But what we were doing here is we were changing the degree of frustration progressively from the non-frustrated limit to the somewhat frustrated limit to the fully frustrated limit, which is a triangular lattice. And we are trying to see what would be the performance of GUAWA on these three limits. And not going into too much into the details of GUAWA, basically there are two parameters there, the beta and the gamma parameter, which are the two angles that you finally start to optimize. And when you have optimized it, you find out for what beta and gamma you get the best probability for the ground state and where you get the worst probability. Once you find that out, then we can get an overall phase diagram that we can draw. And when we draw that phase diagram, this is the probability of ground state versus what are the various phases that you get. The various phases that you get from a ferromagnetic phase, which is G, to some magnetization plateau phases, which are C, D, E, F, to a completely antiferromagnetic phase, which is B and A. So that's how the whole, it's close to the Shastry-Sutherland lattice that we know in the Ising limit. Of course, in this case, we are constrained with the number of qubits that we have. And we embedded that on the Honeywell device, and we were indeed able to find out at what beta and what gamma we have the lowest energies. And from that, we were able to figure out the probability of the various states that we see in the system. And as we see from the results, that the quantum computer more or less gives the so that was a pure state preparation, and this is what we get from the quantum computer. So mostly, for most of the states, we get a good result. So with that, I will end my talk and say that the results from D-Wave and Fujitsu are very consistent with previously known solutions, and it is indeed possible to discover new critical magnetic phases and also map it to real measurements, which is something that we are very interested in. And we want to assess what are the computational benefits of going fully quantum. And that's not only on D-Wave, where we can change the annealing times and do it, but also on other machines, which are gate-based. With that, I will end my talk. Thank you so much.
Great. Well, thank you, Arnab. That was fascinating. And it's really interesting to see how you've been able to merge interesting problems in condensed matter with modern alternative types of computing. Let me start with a question, and then I'll open it to the audience. So, and this relates to perhaps the last point you made on your last slide. In this particular case, the model you said is analytically solvable. And so then that begs the question, so what did we gain by simulating it on D-Wave and Fujitsu and so on? Are there new insights to be had that were not accessible otherwise?
Well, so it is analytically solvable in the true Shastry-Sutherland limit, but real materials are seldom truly Shastry-Sutherland. You have all the sorts of other things which are going on. So the real gain will come when we can go away from the analytical limit. And that's always the case. But the first benchmarking, whether we trust these devices and how much we trust them, has to be done in the limit where we can find the solution in some other way. So the other reason, what we found very nice is that, and this was in the D-Wave system, is that if once we kind of shim things well, once we kind of understand how the qubits are behaving, we understand the annealing parameters well, we get the solution in the very first iteration, which is not something that I'm very used to. I mean, I'm used to doing a Monte Carlo, several iterations, and then you are probably at some solution which you can trust. But here you are right there very quickly, which was very heartening to see. But of course, I mean, comes with the overhead that you have to really understand the system very well. And finally, I will make the point that our goal is to see how we can go beyond just Ising to like the true transverse field Ising universality class. Is that possible? And also with the results from QAOA, I mean, we don't need to probably restrict ourselves to Ising. And then we are getting into the limits where things are not that easily solved. Even you have the sign problem coming in. Of course, for small lattices, you can just exactly diagonalize it and then you're done. But hopefully we will be able to go beyond that as the quantum volumes increase.
Okay, great, thanks. Are there questions from the audience?
Yes, may I ask you a related question?
Sure.
Okay. I understand Fujitsu digital annealer implements simulated annealing of some kind. And I wonder if there is any advantage of using that dedicated machine instead of simulating on the conventional computer.
Absolutely.
On
There
this
is.
problem. On this problem. Yeah.
First, yeah, even on this problem, there is. So once we so what we found is that for the Fujitsu annealer it has a lot more qubits, sorry, a lot more bits, classical bits, and they are all-to-all connected, which means that you can go very complex with the Hamiltonian that you need to solve without really worrying about embedding, which is something you cannot do on the D-Wave machine, for example.
I don't mean the comparison with D-Wave, but comparison with the conventional classical machine software simulating.
Oh, yeah, because it is parallel tempering. I think that what we found is that it is extremely efficient in finding out all the phases. Now, what we have not done is compare with another classical machine side by side where we kind of do it. But we did a little bit of Monte-Carlo ourselves. And when we did that, we found that we always get stuck in kind of some weird phase. And in some clusters, we get the right solution, but we have domains and whatnot when we do a Monte-Carlo. But when we do it on the Fujitsu machine, it just finds the right solution. It just finds a very clean solution in the first attempt. So we trust that solution better. So that's what we have done. So if you're not at the critical point, and if you just want to sit in the middle of all these phases, then we think that the Fujitsu is a very good choice because you will find these magnetic phases very, very fast. But if you are close to the critical point, then I think that it is debatable which is a better machine to use, even Monte-Carlo. If that's better, we don't
understand
know.
Fujitsu machine implements a special type of dynamics which may affect the dynamical exponent, for instance. So I thought we should take some care in the analysis of those.
I think that I agree with you, and we were not looking at the dynamics with the Fujitsu machine close to the phase transition. So close to the phase transition, what happens is that the dynamics are slow. So if you have some inherent dynamics in the Fujitsu machine, that is now going to be, if that becomes in the same time scale of the dynamics of your system, then you start getting wrong results. So what we think is that close to the phase transitions, we have to be careful. But away from the critical points, then it is kind of kosher. It gives us the right solution. So that is what I think. But you are absolutely right.
Thank you. Another question. The D-Wave machine operates at finite temperature. Do you see any trace of it?
We have been asking D-Wave to see if we can change the temperature of the machine in order to find out how much classical is classical, how quantum is quantum. I don't think we have answered that question very well yet. But you are right. I mean, since we are at a finite temperature, it is going to affect the quality of the solutions, again, close to the phase transitions, because at the phase transitions, you have coherence in all the lengths and timescales. And what happens if you have a finite temperature is that it breaks them up, kind of thermally breaks them up. And that means that you will kind of get rounding right close to the phase transition instead of these sharp transitions. Even if the Hamiltonian if the right solution of the Hamiltonian is a sharp transition, you will still get these rounded off transitions there. So that's what happens when you have temperature.
Thank you.
Yeah.
Are there questions from other people? So I have another question for you. If I understood correctly, all the phase trends, all the results you reported here were at essentially the classical phase of this problem. So in the D-wave case, you annealed back to the end where the Hamiltonian is just the Ising term. But did you also try to look at the quantum phase transitions in this model by pausing at s less than 1?
Yeah, the answer is yes, and to be honest, we are still trying to digest. It's still not ready. Those results are still not ready for prime time, but that's one of the very interesting problems looking at the true transverse field Ising universality limit, where it is really quantum. Understand whether it's coming from true quantum scaling or whether it is coming from some other machine parameters. So I think that's the meat.
What about the same question when you don't use D-wave but a gate model machine and do QAOA, some other algorithm?
So I think that what you just asked is really in our mind, and we should really do that because it will be very helpful for the community in general review. We just started on using the QAOA last year, but I think that that's exactly the direction that we want to go. And not only that, I think that it is also important that we take a look into some of the other machines which are based on trapped ions and whatnot, because we can get things like Kibble-Zurich mechanism from those as well. And that is, I think, if we get that, then we know that it's really quantum. And then we are getting to something where we can point our fingers and say that, hey, this is something that it's really interesting. Yeah.
And presumably in the quantum phase, the model is not exactly solvable.
That is absolutely correct. I mean, if we can solve that, like in the number of qubits that you have, then you can arguably think of making some claims about true supremacy. But I absolutely agree. But to be honest, I mean, we are not chasing supremacy as much in this endeavor, at least. I mean, for us, I mean, if we can get good results, which is utilitarian, we would say that that's great, because now we have another way of solving that quantum problem.
Great. Are there any more questions?
No, but you are right that, I mean, the Kibble-Zurich mechanism, I mean, that's what I think it's extremely important, and ways to catch it is something that needs to be researched more.
Okay. I don't see any more questions, so let's thank our speaker.
Yep.
And thanks again, and hope to see you all at the next talk.
And I hope to meet you all one day in person, really. Thank you.
Okay, bye-bye.
Thank you, bye.